The topic of this presentation is Dual-Critic Reinforcement Learning Framework for Frame-Level Application in HEVC H.265. This is the outline. First, I will begin with the introduction, then I will move to the audio basics. After that, I will go through how we address video encoder control from the audio perspective. Next, I will show you our experimental results. Lastly, I will conclude with few concluding remarks. This work presents the AI-assisted video compression for frame-level application of video rate control. It also reflects the potential that how could the modern video codec that benefit from the machine learning. We apply the reinforced learning technique, which lends itself to dependent decision making with the aim to maximizing the long-term reward on constraint optimization. These slides show how good our skin is. As you can see, it achieves better video quality with a similar bit rate compared with H.265. You can visit our website for more examples. Our task is to encode a group of pictures subject to a rate constraint. The question is how to perform bit allocation among these video frames such that sound of the distortion is minimized while satisfying the rate constraint. In fact, we allocate bits by choosing their quantization parameters. The objective function can be written as the arc-mean of the sum of the distortion of a group picture subject to the rate constraint. And this is a constraint optimization problem. What really complex this task is the interframe prediction. This turns this bit allocation among video frames into a dependent decision-making process. Next, we move to reinforced learning basics. This is the basic setup of the reinforcement learning. It involves an agent and the environment. The agent is one that we hope it can learn to do the decision making for us. The training starts with the agent taking the action based on observing some state signal from the environment. Given this action and state, the environment responds with the reward signal indicate how good the action is. At the same time, it also outputs a new state for the agent to take the next action. The process repeats until terminal state is reached. I will learn the policy from trial and error. Let us assume that the policy is just some function parameterized by theta. The function takes the state as input and output probability distribution over actions. The trial and error learning is trained the theta in such a way that it encourages the agent to take action A in state S when this leads to a high long-term reward. DDPG is one of the useful algorithms of the reinforcement learning, and it is the actor-critic approach. The critic is used to learn to estimate the value of the reward goal and explore to find the highest reward goal if possible. Then, the actor updates parameter to output the action that toward the highest reward goal. Next, I will move to the proposed method. This slide shows how we formulate the frame-level application as an R problem. Here, we have the agent play the role of our application algorithm, and the environment is the encoder. The agent begins with observing some state signal for the first video frame. It then decides the QP for the current encoding frame. Then the encoder follows this QP to do the encoding. The process then repeated until a terminal state is reached. In this work, our state signal involves 8 handcrafted signals. The first two are the intra and inter features of the current coding frames, The third and the fourth are the intra and inter features of the remaining frames. The rest are the remaining bits, remaining frames, frame types, and the rate constraint information. The intra-frame features reflect the texture complexity of the video frame by evaluating the mean and the variance of its pixel values. The inter-frame feature reflect the texture complexity resulting from inter-prediction by evaluating the mean and the variance of the frame difference through uni and by prediction. Feature over remaining frames averages intra and inter-frame features over the remaining frames. Now let's turn to the reward signal. Reward is the score given to the agent for the action it takes, and how the reward signal design could crucially determine how the agent behaves. For the immediate distortion reward, the goal is to minimize the sum of the distortion of the GOP. Here, the MSQP0 and MSEQP51 are the two extreme GOP level MSE value to normalize the MSE of the current frame. And it is divided by the GOP size that limits the cumulative reward between 0 to 1. The negative sign suggests that our intent is to minimize the distortion by maximizing the reward. For the immediate rate reward, the goal is to minimize the encoding bitrate error. We set the negative rate bias at the last video frame in the GOP and the 0 otherwise. Since we have two separate rewards, we propose a dual-critic reinforced learning framework for frame-level allocation. We introduce two separate critics. The distortion critics learns to predict the distortion reward goal, while the rate critics learns to predict the rate reward goal. And the actor will choose one of the critics to update itself. This slide reminds you what the distortion reward goal and rate reward goal that distortion and rate critics are learned to predict. Once the critics can well predict the reward goal, the next question is how the Dual-Critic algorithm update the actor. We use the latest policy to encode a GOP. If the actual encoding bit is greater than the target bit, RGOP, we use the rate critic to update the actor to minimize the rate bias. If the actual encoding bit is less than the target bit, we use the distortion critic to update the actor to minimize the distortion. This is our Dual-Critic algorithm. The first three lines are the initialization. From line 5 to line 18, we update the rate and distortion critics, and we use noise to explore the best rate and the distortion reward goal. After line 20, we update the actor. In order to choose the correct critic for training the actor, we encode the GOP by using the latest current policy to check if it is overflow or underflow. If it is underflow, we use distortion critic, and if it is overflow, we use rate critic. This slide compares the single critic with dual critic. Different from our dual critics, single critic will mix the rate reward and the distortion reward into a single reward function. For single reward approach, it is common to introduce a hyperparameter lambda to balance the rate and the distortion. However, how to choose the lambda that works well on every test sequence is a non-trivial problem. For an overall comparison, single-critic has better convergence, but shows poor generalization due to the ad hoc mixture of the distortion and the rate goal. As for Dual-Critics, it has better generalization to various test sequences, but it does not guarantee to have convergence. To improve the convergence, we apply the base module into our agent to limit the exploration space. The base module is supervisively trained by using the QPL value of H.265 as the target. As our actor module only need to explore in the limited range to find the optimal solution. Next, I'll move to the experimental results. We experiment our scheme on H.265 with 3-level hierarchical B structure. The GOP size is 16. This slide shows how we get our target bit rate. First, we encode every sequence with fixed QP to get the sequence level bit rate. Next, we turn on the rate control of H.265 for 1 pass and 2 pass. Finally, we observe the GOP level bit rate of H.265 and use this bit rate as our GOP target bit rate. For more details, we use 4 separate models for 4 target bit rates. And for a fair comparison, both of our Dual-Critics method and the single-critic method operate with the same base module. We apply BDPSR and the rate deviations as our evaluation metrics. Our training dataset has 32 videos, and we test on another 9 test videos. To speed up the training, all videos are downsized to 512 times 320. Next, I'll move to the rate distortion performance. This slide shows the RD performance comparison with our Dual-Critics, single-critics, and H.265 one-pass approach. It can be observed that our approach outperforms other methods. Besides, single-critic approach shows good results on more static sequences, but poor results on more dynamic sequences. It is because Chen and others use a fixed type of parameter lambda for all the videos, which cannot be generalized well for all the videos. The BDPS table double confirmed the RD performance. Our method has a 0.91 dB gain compared with the one-pass H.265, while the single-critic only has the 0.39 dB of the gain. For rate deviation, our Dual-Critic approach shows comparable number compared with the single-critic method. This slide shows subject quality comparison. As you can see, our scheme has the lowest residual compared with the other methods. And this is another example. As you can see, our model still shows the smallest residual signal. This slide shows the RT performance compared with our Dual-Critics, single-critics, and H.265 two-pass approach. Since the two-pass is a more stronger approach, in this time, our Dual-Critic method shows a comparable result compared with the two-pass H.265. From the BDPSR model, only has a 0.06 dB gain compared with 2-pass H.265. Next, I'll move to the encoding runtime. The runtime of our model is comparable with H.265 1-pass and half of the runtime compared with H.265 2-pass. Finally, I will show you our QP assignment. This slide shows the QP assignment for the fast motion sequences. Our model tends to use smaller QP for the I and capital B frames and higher QP for the small b frames. It is reasonable since I and capital B frames are served as the reference frames. One of the interesting observations is that our model tends to choose larger QP for the second half of the small b frames. Since we do not impose any constraint on their quality distribution, and the small b frames are non-reference frames, this unbalanced b frames behavior turned out to be the solution that the model learned. This slide shows the QP assignment for the slow motion sequences. Our model tends to use smaller QP for the I frame and a larger QP for the capital B and the small b frames. The conclusions. This work introduced a dual-critic RL framework for frame-level allocation. It overcomes the need of combining the rate and the distortion rewards in a heuristic manner. Our method achieves promising RD performance and a very precise rate control accuracy. Thank you for your attention.